Now, as I said before, I wanna prove click decision problem CDP as NP complete. In fact, to prove it, first of all, we must prove CDP as an MP, and then we must prove it as MP hard. First, let's prove it as MP, as in MP. So by looking to that graph, we have A B C D E F. If we could find a click of size k, and all of the edges that consist that click is belong to that graph, this means that we verify that it's MP. So by looking to that graph, we'll notice that, or we remark that BCEF, that subgraph, it's a complete subgraph, and it's a maximal subgraph, or a maximal click of size k 4. Let's suppose that k is 4. So by and all of the edges that consist that click is belong to the, or are belong to the whole graph. So for this reason, we can prove that that we can say that we found a click of size k, and all of edges and the vertices are found in the whole graph, and then we can prove that click for that graph is in MP. Now, the next step, we must prove CDP as MP hard. To prove that, we must find a problem which is already proved as MP hard. Let's suppose that we have P1 and our problem is P2. If we could reduce P1 to P2, this means that if we could find a solve for P2, also we will have a solve for P1. And if P1 is MP hard, also P2 will be MP hard. Actually, one of the most, or let's say, if we could find the MP hard problem, which is already proves that, so we will adopt SAT, which is approved proved as MP hard. And our problem is CTP. So we must reduce SAT to CTP. If we could achieve and that reduction must be done in polynomial time. So if we could, and since SAT is MP hard, also CTP will be MP hard. So we will take from SAT instance, or let's say we will take a formula which is conjunctive form formula from SAT, and from that formula we must prepare a graph of CTP, and then if we could prepare that graph, this means that we could achieve that reduction. Now, when we reduce SAT to CTP, we want to form a conjunctive form formula from SAT. We will choose a set of variables x1, x2, x3. So our formula will be like this: if x1 or x2 and x1 dash or x2 dash and x1 or x3. Now we have here three clauses: clause 1, clause 2, and clause 3. So our formula is made of like this. It's a set of clauses Ci, where I from 1 to k. Here k is 3, k of size 3, and we have three clauses. This means that we have three clauses, so k is 3. So from that formula we will prepare our graph. So let's take x1 and x2. Here we have x1 dash and x2 dash, and here we have x1 and x3. So here x1 belong to clause 1 and x2 belong to clause 1 also. X2 x1 dash belong to clause 2, here clause 2, and here clause 1, and here clause clause 3, and here clause 3. So this is our graph. So our graph which we must prepare it is about a set of vertices a it's ai, where a belongs to clause I. Now we will connect the vertices with each other. Before making the edges between the vertices, we must know two rules. The first rule, we cannot connect x1 with its negation. This means that we cannot connect x1 with x1 dash. The second rule, we cannot connect two vertices belonging to the same clause. This means that we cannot connect x1 with x2. So according to the rules I said, we cannot connect this. We can connect x1 with x2 dash, and we can x1 with x1, this x1, and we will connect x1 with x3. And x2 with x1 dash, yes, it's allowed. X2 with x2 dash, we cannot. X2 with x1, yes, we can. And x2 with x3, yes, we can. Also, x1, we can connect it with x2 dash, yes. X1 with x1 dash, we cannot. X3 with x2 dash, yes, we can. X3 with x1 dash, we cannot. We can connect it. So our graph is connected. The vertex is connected with each other. So the edges of our graph, it will consist of ai and bj. So where I must not equal to j. This means that we cannot connect between two vertices from the same clause. And also b mustn't be the negation of a, because we cannot connect x1 with x1 dash. Now, if we want to find a solve for that graph, or let's say if we want to solve for CDB, so we must find and we must extract from here a clique of size k, where k is indicated by the number of clauses of our formula, which we adopted from SAT. So we must since we have here three clauses, so this means that we must find a clique of size 3 in order to find a solve, or in order to prove that there is a solve for that graph. So by looking to that graph, we can remark that x1 dash and x1 dash, x2 and x3, this is a connected subgraph of that graph, and it's a clique of size 3 of the number of clauses. And by the way, if we look to that graph, we cannot find a clique of size bigger than the number of clauses of our formula. So we cannot find a clique, for example, of size 4, for example. The maximum clique is of size 3. So, and also maybe we will have many cliques of size 3, not just that clique, but we will adopt, for example, that clique x1 dash, x2 and x3. This is our clique. Now, as I said, this is our clique. Now, if we can say that, or if we want to say that SAT is reduced to CDB, this means that we must prove that for each, or let's say yes, for each clique for each click of size k of size 3, for each click of size 3 which is consisted inside through that graph must satisfy that formula. This means that x1 dash, x2 and x3, this is click of size 3, and x2 dash, x1, x3, that click also, and all the other clicks of size k must satisfy that formula and make it true, and make that the result of that formula is true. If we could prove all of them satisfy that formula and make it true, so we can say that SAT is reduced to CDP, and then we can say that we found a solution for CDP and prove it as MP and MP hard. So by taking as I said x1 dash, x2, x3, now x1 is 0 and x2 is 1, x3 is 1. So we will apply those values in our formula. x1 is 0 and x2 is 1. So 0 or 1 is 1, and x1 dash 0, but because it's dash, so 0 dash it will be 1. x2 this 1 dash it will be 0, so 1 or 0 it's 1. Also x1 this x1 0 and x3 is 1, so 0 or 1 is 1. Now since between all the clauses is and, so 1 and 1 is 1 and 1 and 1 is 1, so the result is true. So we proved that for that click can satisfy that problem, can satisfy that formula and make it true, and also for all the other clicks must, and it's already proved, or it's all of them can satisfy that formula and make it true. Now let's try another click, x2 dash, x3, x1, also it's a click of size 3. So the value it will be x1 it will be 0, and x2 it will be x1 it will be 1, and x2 will be 0, and x3 will be 1. So let's satisfy, or let's apply those values on our formula. So x1 it will be 1 or x2 0, so the result it will be 1 or 0 it's 1, and x1 dash it will be, because 1, so it will be 0, x2 dash it will be 1, so 1 or 0 or 1 it will be 1, and x1 is 1, so x1 is 1, and x3 is 1, is already 1, is 1, so 1 or 1 also is 1, so 1 and 1 and 1 and 1, so the result it will be 1. So by applying all the clicks from that graph, we could say that that graph satisfy that formula, and we could, and then we can say that we reduce SAT to CDP. This means that we prepared the targeted graph, and since SAT is already proved as MP hard, so CDP also is MP hard, and that reduction reduction is done in polynomial time. And that's it. We proved CDP as MP hard. Since we prove it MP and prove it as MP hard, so we can say now CDP is MP complete, and that's it.